Hello everyone, and welcome to the next module in this course, which is covering natural language processing with recurrent neural networks. Now what we're going to be doing in this module here is first off discussing what natural language processing is, which I guess I'll start with here. Essentially, for those of you that don't know, natural language processing, or NLP for short, is the field or discipline in computing or machine learning that deals with trying to understand natural or human languages. Now, the reason we call them natural is because these are not computer languages or programming languages per se, and actually computers are quite bad at understanding textual information and human languages, and that's why we've come up with this entire discipline focused on how they can do that. So we're going to do that using something called recurrent neural networks, but some examples of natural language processing would be something like spell check, autocomplete, voice assistance, translation between languages. There's all different kinds of things, chatbots, but essentially anything that deals with textual data. So like paragraphs, sentences, even words, that is probably going to be classified under natural language processing in terms of doing some kind of machine learning stuff with it. Now, we are going to be talking about a different kind of neural network in this series called recurrent neural networks. Now, these are very good at classifying and understanding textual data, and that's why we'll be using them, but they are fairly complex, and there's a lot of stuff that goes into them. Now, in the interest of time and just not knowing a lot of your math background, I'm not going to be getting into the exact details of how this works on a lower level, like I did when I explained kind of our, I guess, fundamental learning algorithms, which are a bit easier to grasp, and even just regular neural networks in general. We're going to be kind of skipping over that and really focusing on why this works the way it does, rather than how and when you should use this. And then maybe understanding a few of the different kinds of layers that have to do with recurrent neural networks. But again, we're not going to get into the math. If you'd like to learn about that, there will be some sources at the bottom of the guide, and you can also just look up recurrent neural networks and you'll find lots of resources that explain all of the fancy math that goes on behind them. Now, the exact applications and kind of things we'll be working towards here is sentiment analysis. That's the first kind of task or thing we're going to do. We're actually going to use movie reviews and try to determine whether these movie reviews are positive or negative by performing sentiment analysis on them. Now, if you're unfamiliar with sentiment analysis, we'll talk about it more later, but it essentially means trying to determine how positive or negative a sentence or piece of text is, which you can see why that would be useful for movie reviews. Next, we're going to do character/text generation. So essentially, we are going to use a natural language processing model, I guess if you want to call it that, to generate the next character in a sequence of text for us. And we're going to use that model a bunch of times to actually generate an entire play. Now, I know this seems a little bit ridiculous compared to some of the trivial examples we've done before. This will be quite a bit more code than anything we've really looked at yet, but this is very cool because we're actually going to train a model to learn how to write a play. That's literally what it's going to do. It's going to read through a play, I believe it's Romeo and Juliet, and then we're going to give it a little prompt when we're actually using the model and say, okay, this is the first part of the play, write the rest of it. And then it will actually go and write the rest of the characters in the play, and we'll see that we can get something that's pretty good using the techniques that we'll talk about. So the first thing that I want to do is talk about data. So I'm going to hop onto my drawing tablet here, and we're going to compare the difference between textual data and numeric data like we've seen before, and why we're going to have to employ some pretty complex and different steps to turn something like this, a block of text, into some meaningful information that our neural network's actually going to be able to understand and process. So let's go ahead and get over to that. Okay, so now we're going to get into the problem of how we can turn some textual data into numeric data that we can feed to our neural network. Now, this is a pretty interesting problem, and we'll kind of go through, as we start going through it, you should see why this is interesting and why there's a lot of difficulties with the different methods that we pick. But the first method that I want to talk about is something called bag of words, in terms of how we can kind of encode and pre-process text into integers. Now, obviously, I'm not the first person to come up with this. Bag of words is a very famous, almost I want to say, algorithm or method of converting textual data to numeric data, although it is pretty flawed and it only really works for simple tasks. And we're going to understand why in a second. So we're going to call this bag of words. Essentially, what bag of words says is what we're going to do is we're going to look at our entire training data set, right? Because we're going to be turning our training data set into a form the network can understand. And we're going to create a dictionary lookup of the vocabulary. Now, what I mean by that is we're going to say that every single unique word in our data set is the vocabulary, right? That's the amount of words that the model is expected to understand, because we're, going to show all those words to the model. And we're going to say that every single one of these words, so every single one of these words in the vocabulary, is going to be placed in a dictionary. And beside that, we're going to have some integer that represents it. So for example, maybe the vocabulary of our data set is the words, I, a, maybe Tim, maybe day, me, right? We're gonna have a bunch of arbitrary words. I'll just put ... to show that this kind of goes to the length of the vocabulary. And every single one of these words will be placed in a dictionary, which we're just gonna call kind of our lookup table or our word index table. And we're gonna have a number that represents every single one of them. So you can imagine that in very large data sets, we're going to have, tens of thousands of hundreds of thousands, sometimes even maybe millions of different words, and they're all going to be encoded by different integers. Now, the reason we call this bag of words is because what we're actually going to do when we look at a sentence is we're only going to keep track of the words that are present and the frequency of those words. And in fact, what we'll do, is we'll create what we call a bag. And whenever we see a word appears, we'll simply add its number into the bag. So if I have a sentence like, I am Tim day, I'm just going to do like a random sentence like that. Then what we're going to do is every time we see a word, we're going to take its number and throw it into the bag. So we're going to say, all right, I, that's 0, am, that's 1, Tim, that's 2, day, that's 3. That's 3 again. And notice that what's happening here is we're losing the ordering of these words, but we're just keeping track of the frequency. Now, there's lots of different ways to kind of format how we want to do bag of words, but this is the basic idea. I'm not going to go too far in because we're not actually really going to use this technique, but essentially you lose the ordering in which words appear, but you just keep track of the frequency and what words appear. So this could be very useful when you're looking, you're doing very simple tasks where the presence of a certain word will really influence the kind of type of sentence that it is or the meaning that you're going to get from it. But when we're looking at more complex input, where, different words have different meanings depending on where they are in a sentence, this is a pretty flawed way to encode this data. Now, I won't go much further into this. This is not the exact way the bag of words works, but I just wanted to show you kind of an idea here, which is we just encode every single unique word by an integer, and then we don't even really care about where these words are. We just throw them into a bag and we say, all right, if this is our bag right here that I'm doing the arrow to, we'll just throw in 3 as many times as, the word day appears. We'll throw in 1 as many times as the word, am appears, and so on and so forth. And then what will happen is we'll feed this bag to our neural network in some form, depending on the network that we're using, and it will just look at and say, okay, so I have all these different numbers, that means these words are present, and try to do something with it. Now I'm going to show you a few examples of where this kind of breaks down, but just understand that this is how this works. This is the first technique called bag of words, which again, we will not be using. So what happens when we have a sentence where the same word conveys a very different meaning, right? And I think I have an example on the slides here that I'll go into. Yes, so like this. Okay, so for our bag of words technique, which we can kind of see here, and maybe we'll go through it, let's consider the two sentences. Where are they? Here. I thought the movie was going to be bad, but it was actually amazing, and I thought the movie was going to be amazing, but it was actually bad, right? So consider these two sentences. Now, I know you guys already know what I'm going to get at, but essentially these sentences use the exact same words. In fact, they use the exact same number of words, the exact same words in total, and, well, they have a very different meaning. With our bag of words technique, we're actually going to encode these two sentences using the exact same representation. Because remember, all we do is we care about the frequency and what words appear, but we don't care about where they appear. So we end up losing that meaning from this sentence because the sentence, I thought the movie was going to be bad, but it was actually amazing, is encoded and represented by the same thing as this sentence is. So that, obviously is an issue, that's a flaw, and that's one of the reasons why bag of words is not very good to use, because we lose the context of the words within the sentence. We just pick up the frequency and the fact that these words exist. So that's the first technique, that's called bag of words. I've actually written a little function here that does this for us. This is not really the exact way that we would write a bag of words function, but you kind of get the idea that when I have a text, this is a test to see if this test will work is test AA. I just did a bunch of random stuff so we could see. What I'm doing is printing out the bag, which I get from this function, and you guys can look at this if you kind of want to see how this works. And essentially what it tells us is the word 1 appears 2 times. Yes, the word 2 appears 3 times, the word 3 appears 3 times, the word 4 appears 3 times, 5 once, 6 once, 7 once, so on. That's the information we get from our bag, right, from that encoding. And then if we look up here, this is our vocabulary, so this stands for 1, is 2, A is 3, so on, and you can kind of get the idea from that. So that is how we would use bag of words, right? If we did an encoding kind of like this, that's what that does, and that's one way of encoding it. Now I'm going to go back and we'll talk about another method here as well, actually a few more methods before we get into anything further. Alright, so I'm sure a lot of you were looking at the previous example I did, and you saw the fact that what I did was completely remove the idea of kind of sequence or ordering of words, right? And what I did was just throw everything in a bag, and I said, alright, we're just going to keep track of the fact that we have, 3 A's, or we have 4 thes, or 7 Tims, right? And we're just going to lose the fact that, words come after one each other, and we're going to lose their ordering in the sentence, and that's how we're going to encode it. And I'm sure a lot of you are saying, well, why don't we just not lose the ordering of those words? We'll just encode every single word with an integer and just leave it in its space where it would have been in the original string. Okay, good idea. So what you're telling me to do is something like this. Tim is here will be our sentence. Let's say we encode the word Tim with 0, is 1, here is 2, and then that means our translation goes 0, 1, 2. And that means, right, if we have a translation, say like 2, 1, 0, even though these use the exact same number of words and exact same representation for all these words, well, this is a different sentence, and our model should be able to tell that because these words come in a different order. And to you, good point if you made that point, but I'm going to discuss where this falls apart as well and why we're not going to use this method. So although this does solve the problem I talked about previously, where we're going to kind of lose out on the context of a word, there still is a lot of issues with this, and they come especially when you're dealing with very large vocabularies. Now let's take an example where we actually have a vocabulary of say 100,000 words. And we know that that means we're going to have 100,000 unique mappings from words to integers. So let's say our mappings are something like this. 1 maps to the string happy, the word happy, right? 2 maps to sad, and let's say that the string 100,000, or the number 100,000, maps to the word, I don't know, let's say good. Now we know as humans, by kind of just thinking about, let's consider the fact that we're going to try to classify sentences as say positive or negative, so sentiment analysis, that the words happy and good in that regard, sentiment analysis, are probably pretty similar words, right? And then if we were going to group these words, we'd probably put them in a similar group, we'd classify them as similar words, we could probably interchange them in a sentence and it wouldn't change the meaning a whole ton. I mean, it might, but it might not as well. And that we could say these are kind of similar. But our model, or our encoder, right, whatever we're doing to translate our text into integers here, has decided that 100,000 is going to represent good and 1 is going to represent happy. And well, there's an issue with that, because that means when we pass in something like 1 or 100,000 to our model, it's going to have a very difficult time determining the fact that 1 and 100,000, although they're 99,999 kind of units apart, are actually very similar words. And that's the issue we get into when we do something like this, is that the numbers we decide to pick to represent each word are very important, and we don't really have a way of being able to look at words, group them, and saying, okay, well, we need to put all of the happy words in the range like 0 to 100, all of the like adjectives in this range. We don't really have a way to do that. And this gets even harder for our model when we have these arbitrary mappings, right? And then we have something like 2 in between, where 2 is very close to 1, right? Yet these words are complete opposites. In fact, I'd say they're probably polar opposites. Our model trying to learn that the difference between 1 and 2 is actually way larger than the difference between 1 and 100,000 is going to be very difficult. And say it's even able to do that, as soon as we throw in the mapping 900, right? The 99,900, we put that as bad. Well, now it gets even more difficult because it's now like, okay, well, if the range is this big, then that means these words are actually very similar. But then you throw another word in here like this and it messes up the entire system. So that's kind of what I wanted to show, is that that's where this breaks apart on these large vocabularies. And that's why I'm going to introduce us now to another concept called word embeddings. Now, what word embeddings does is essentially try to find a way to represent words that are similar using very similar numbers. And in fact, what a word embedding is actually going to do, and I'll talk about this more in detail as we go on, is classify or translate every single one of our words into a vector. And that vector is going to have some, n amount of dimensions. Usually we're going to use something like 64, maybe 128 dimensions for each vector. And every single component of that vector will kind of tell us what group it belongs to or how similar it is to other words. So let me give you an idea what I mean. So we're going to create something called a word embeddings. Now, don't ask why it's called embeddings. I don't know the exact reason, but I believe it's has to do something with the fact that they're vectors. And let's just say we have a 3D plane like this, and we've already kind of looked at what vectors are before, so I'll skip over explaining them. And what we're going to do is take some word. So let's say we have the word good. And instead of picking some integer to represent it, we're going to pick some vector, which means we're going to draw some vector in this 3D space. Actually, let's make this a different color. Let's make this vector say red, like this. And this vector represents this word good. And in this case, we'll say we have x1, x2, x3 as our dimensions, which means that every single word in our data set will be represented by 3 coordinates, so one vector with 3 different dimensions, where we have x1, x2, and x3. And our hope is that by using this word embeddings layer, and we'll talk about how it accomplishes this in a second, is that we can have vectors that represent very similar words being very similar, which means that, if we have the vector good here, we would hope the vector happy from our previous example, right, would be a vector that points in a similar direction to it, that is kind of a similar looking thing, where the angle between these two vectors, right, and maybe I'll draw it here so we can see, is small so that we know that these words are similar. And then we would hope that if we had a word that was much different, maybe say like the word bad, that would point in a different direction, the vector that represents it, and that would tell our model, because the angle between these two vectors is so big, that these are very different words, right? Now, in theory, does the embedding layer work like this? Not always, but this is what it's trying to do, is essentially pick some representation in a vector form for each word, and then these vectors, we hope, if they're similar words, are going to be pointing in a very similar direction. And that's kind of the best explanation of a word embeddings layer I can give you. Now, how do we do this though? How do we actually, go from word to vector and have that be meaningful? Well, this is actually what we call a layer. So word embeddings is actually a layer, and it's something we're going to add to our model. And that means that this actually learns the embeddings for our words. And the way it does that is by trying to kind of pick out context in the sentence and determine, based on where a word is in a sentence, kind of what it means, and then encodes it doing that. Now, I know that's kind of a rough explanation to give to you guys. I don't want to go too far into word embeddings in terms of the math, because I don't want to get, waste our time or get too complicated if we don't need to. But just understand that our word embeddings are actually trained, and that the model actually learns these word embeddings as it goes. And we hope that by the time it's looked at enough training data, it's determined really good ways to represent all of our different words so that they make sense to our model in the further layers. And we can use pre-trained word embedding layers if we'd like, just like we used that pre-trained convolutional base in the previous section. And we might actually end up doing that. Actually, probably not in this tutorial, but it is something to consider that you can do that. So that's how word embeddings work. This is how we encode textual data. And this is why it's so important that we kind of consider the way that we pass information to our neural network, because it makes a huge difference. Okay, so now that we've talked about kind of the form that we need to get our data in before we can pass it further in the neural network, right? Before it can get past that embedding layer, before it can get put into any dense neurons, before we can even really do any math with it, we need to turn it into numbers, right? Our textual data. So now that we know that, it's time to talk about recurrent neural networks. Now, recurrent neural networks are the type of networks we use when we process textual data typically. You don't always have to use these, but they are just the best for natural language processing, and that's why they're kind of their own class, right? Now, the fundamental difference between a recurrent neural network and something like a dense neural network or a convolutional neural network is the fact that it contains an internal loop. Now, what this really means is that the recurrent neural network does not process our entire data at once. So it doesn't process the entire training example or the entire input to the model at once. What it does is processes it at different time steps and maintains what we call an internal memory and kind of an internal state, so that when it looks at a new input, it will remember what it's seen previously. Are just the best for natural language processing, and that's why they're kind of their own class, right? Now, the fundamental difference between a recurrent neural network and something like a dense neural network or a convolutional neural network is the fact that it contains an internal loop. Now, what this really means is that the recurrent neural network does not process our entire data at once. So it doesn't process the entire training example or the entire input to the model at once. What it does is processes it at different time steps and maintains what we call an internal memory and kind of an internal state, so that when it looks at a new input, it will remember what it's seen previously and treat that input based on kind of the context or the understanding it's already developed. Now, I understand that this doesn't make any sense right now, but with a dense neural network, or the neural networks we looked at so far, we call those something called feed-forward neural networks. What that means is we give all of our data to it at once, and we pass that data from left to right, or I guess for you guys, from left to right. So we give all of the information, we would pass those through the convolutional layer to start. Maybe we would pass them through dense neurons, but they get given all of the info, and then that information gets translated through the network to the very end, again, from left to right. Whereas here with recurrent neural networks, we actually have a loop, which means that we don't feed the entire textual data at once. We actually feed one word at a time. It processes that word, generates some output based on that word, and uses the internal memory state that it's keeping track of to do that as part of the calculation. So essentially the reason we do this is because just like humans, when we, look at text, we don't just take a photo of this text and process it all at once. We read it left to right, word to word, and based on the words that we've already read, we start to slowly develop an understanding of what we're reading, right? If I just read the word now, that doesn't mean much to me. Or if I just read the word encode, that doesn't mean much. Whereas if I read the entire sentence, now that we've learned a little bit about how we can encode text, I start to develop an understanding about what this next word means based on the previous words before it, right? And that's kind of the point here, is that this is what a recurrent neural network is going to do for us. It's going to read one word at a time and slowly start building up its understanding of what the entire textual data means. And this works in kind of a more complicated sense than that. We'll draw it out a little bit, but this is kind of what would happen if we unraveled a recurrent layer. Because a recurrent neural network, yes, it has a loop in it, but really the recurrent aspect of a neural network is the layer that implements this recurrent functionality with a loop. Essentially what we can see here is that if we're saying X is our input and H is our output, xt is going to be our input at time t, whereas ht is going to be our output at time t. If we had a text of, say, length 4, so 4 words, like we've encoded them into integers now at this point, the first input at time 0 will be the first word into our network, right? Or the first word that this layer is going to see. And then the output at that time is going to be our current understanding of the entire text after looking at just that one word. Next, what we're going to do is process input 1, which will be the next word in the sentence, but we're going to use the output from the previous kind of computation or the previous iteration to do this. So we're going to process this word in combination with what we've already seen and then have a new output, which hopefully should now give us an understanding of what those 2 words mean. Next, we'll go to the third word and so forth and slowly start building our understanding of what the entire textual data means by building it up one by one. The reason we don't pass the entire sequence at once is because it's very, very difficult to just kind of look at this huge blob of integers and figure out what the entire thing means. If we can do it one by one and understand the meaning of specific words based on the words that have came before it and start learning those patterns, that's going to be a lot easier for our neural network to deal with than just passing it all at once, looking at it and trying to get some output. And that's why we have these recurrent layers. There's a few different types of them, and I'm going to go through them and then we'll talk a little bit more in depth of how they work. So the first one is called long short-term memory. And actually, in fact, before we get into this, let's talk about just a simple layer so that we kind of have a reference point before going here. Okay, so this is kind of the example I want to use here to illustrate how a recurrent neural network works in a more, I don't know, teaching style rather than what I was doing before. So essentially, the way that this works is that this whole thing that I'm drawing here, right, all of this circle stuff is really one layer. And what I'm doing right now is breaking this layer apart and showing you kind of how this works in a series of steps. So rather than passing all the information at once, we're going to pass it as a sequence, which means that we're going to have all these different words and we're going to pass them one at a time to the layer, right, to this recurrent layer. So we're going to start from this left side over here. So let's write, start over here at time step 0. That's what 0 means. So time step is just, the order. In this case, this is the first word. So let's say we have the sentence, "Hi, I am Tim," right? We've broken these down into vectors. They've been turned into their numbers. I'm just writing them here so we can kind of see what I mean in like a natural language. And they are the input to this recurrent layer. So all of our different words, right? That's how many kind of little cells we're going to draw here, is how many words we have in this sequence that we're talking about. So in this case, we have 4, right? 4 words. So that's why I've drawn 4 cells to illustrate that. Now what we do is at time step 0, the internal state of this layer is nothing. There's no previous output. We haven't seen anything yet, which means that this first kind of cell, which is what I'm looking at right here, what I'm drawing in this first cell, is only going to look and consider this first word and kind of make some prediction about it and do something with it. We're going to pass "hi" to this cell. Some math's going to go on in here. And then what it's going to do is it's going to output some value, which tells us something about the word "hi," right? Some numeric value. We're not going to talk about what that is, but there's going to be some output. Now, what happens is after this cell has finished processing this, so this one's done, this is completed, H0, the output's there. We'll do a check mark to say that that's done, it's finished processing. This output gets fed into actually the same thing again. We're kind of just keeping track of it. And now what we do is we process the next input, which is I, and we use the output from the previous cell to process this and understand what it means. So now, technically, we should have some output from the previous cell. So from whatever "hi" was, right? We do some analysis on the word "I." We kind of combine these things together, and that's the output of this cell, is our understanding of not only the current input, but the previous input with the current input. So we're slowly kind of building up our understanding of what this word "I" means based on the words we saw before. And that's the point I'm trying to get at, is that this network uses what it's seen previously to understand the next thing that it sees. It's building a context. It's trying to understand not only the word, but what the word means, in relation to what's come before it. So that's what's happening here. So then this output here, right? We get some output. We finish this. We get some output H1. H1 is passed into here, and now we have the understanding of what "hi." Now finally, we take the output with this, the output, because it's hard for it to remember what it's seen at the very beginning, because that is now so insignificant. There's been so many outputs tacked onto that it's hard for it to go back and see that, if that makes any sense. Okay, so what I'm going to do now is try to explain the next layer we're going to look at, which is called LSTM. So the previous layer we just looked at, the recurrent layer, was called a simple RNN layer. So simple recurrent neural network layer, whatever you want to call it, right? Simple recurrent layer. Now we're going to talk about the layer, which is LSTM, which stands for long short-term memory. Now, long and short are hyphenated together, but essentially what we're doing, and it just gets a little bit more complex, but I won't go into the math, is we add another component that keeps track of the internal state. So right now, the only thing that we were tracking as kind of our internal state, as the memory for this model, was the previous output. So whatever the previous output was, so for example, at time 0 here, there was no previous output, so there was nothing being kept in this model. But at time 1, the output from this cell right here was what we were storing. And then at cell 2, the only thing we were storing was the output at time 1, right? And we've lost now the output from time 0. What we're adding in long short-term memory is an ability to access the output from any previous state at any point in the future when we want it. Now what this means is that rather than just keeping track of the previous output, we'll add all of the outputs that we've seen so far into what I'm going to call my little kind of conveyor belt that's going to run at the top up here. I know it's kind of hard to see, but it's just what I'm highlighting. It's almost just like a lookup table that can tell us the output at any previous cell, you know, that we want. So we can kind of add things to this conveyor belt, we can pull things off, we can look at them, and this just adds a little bit of complexity to the model. It allows us to not just remember the last state, but look anywhere at any point in time, which can be useful. Now, I don't want to go into much more depth about exactly how this works, but essentially, you know, just think about the idea that as the sequence gets very long, it's pretty easy to forget the things we saw at the beginning. So if we can keep track of some of the things we've seen at the beginning and some of the things in between on this little conveyor belt, and we can access them whenever we want, then that's going to make this probably a much more useful layer, right? We could look at the first sentence and the last sentence of a big piece of text at any point that we want, and say, okay, you know, this tells us X about the meaning of this text, right? So that's what this LSTM does. Again, I don't want to go too far. We've already spent a lot of time kind of covering, you know, recurrent layers and how all this works. Anyways, if you do want to look it up, some great mathematical definitions. Again, I will source everything at the bottom of this document so you can go there. But again, that's LSTM, long short-term memory. That's what we're going to use for some of our examples, although simple RNN does work fairly well for shorter length sequences. And again, remember, we're treating our text as a sequence now, where we're going to feed each word into the recurrent layer, and it's going to slowly start to develop an understanding as it reads through each word, right, and processes that. Okay, so now we are on to our first example where we're going to be performing sentiment analysis on movie reviews to determine whether they are positive reviews or negative reviews. Now, we already know what sentiment means. That's essentially what I just described. So picking up, you know, whether a block of text is considered positive or negative. And for this example, we're going to be using the movie review dataset. Now, as per usual, this is based off of this TensorFlow tutorial / guide. I found this one kind of confusing to follow on the TensorFlow website, but obviously you can follow along with that if you prefer that version over mine. But anyways, we're going to be talking about the movie review dataset. So this dataset is straight from Keras, and it contains 25,000 reviews, which are already pre-processed and labeled. Now what that means for us is that every single word is actually already encoded by an integer, and in fact they've done kind of a clever encoding system where what they've done is said, if a character is encoded by, say, integer 0, that represents how common that word is in the entire dataset. So if an integer was encoded by, or not integer, a word was encoded by integer 3, that would mean that it is the third most common word in the dataset. And in this specific dataset, we have a vocabulary size of 88,584 unique words, which means that something that was classified as this, so 88,584, would be the least common word in the dataset. So something to keep in mind, we're going to load in the data set and do our imports just by hitting run here. And as I've mentioned previously, I'm not going to be typing this stuff out. It's kind of a waste of time. I don't have all the syntax memorized. I would never expect you guys to memorize this either. But what I will do is obviously walk through the code step by step and make sure you understand why it is that we have what we have here. Okay, so what we've done is define the vocabulary size, the max length of a review, and the batch size. Now what we've done is just loaded in our data set by defining the vocabulary size. So this is just the words it will include. So in this case, all of them. Then we have train data, train labels, test data, test labels. And we can look at a review and see what it looks like by doing something like this. So this is an example of our first review. We can see kind of the different encodings for all of these words. And this is what it looks like. They're already in integer form. Now, just something to note here is that the length of our reviews are not unique. So if I do the len of trained data, I guess I wouldn't say unique, but I mean, they're just all different. So the len of trained data 0 is different than the len of trained data 1, right? So that's something to consider as we go through this and something we're actually going to have to handle. Okay, so more pre-processing. So this is what I was talking about. If you have a look at our loaded in reviews, we'll notice they are of different lengths. This is an issue. We cannot pass different length data into our neural network, which is true. Therefore, we must make each review the same length. Okay, so what we're going to do for now is we're actually going to pad our sequences. Now, what that means is we're going to follow this kind of step that I've talked about here. So if the review is greater than 250 words, we will trim off extra words. If the review is less than 250 words, we'll add the necessary amount of, this should actually be zeros in here. Let's fix this, of zeros to make it equal to 250. So what that means is we're essentially going to add some kind of padding to our review. So in this case, I believe we're actually going to pad to the left side, which means that say we have a review of length, 200, we're going to add 50 just kind of blank words, which will represent with the index 0 to the left side of the review to make it the necessary length. So that's good. We'll do that. So if we look at trained data and test data, what this does is we're just going to use something from Keras, which we've imported above. So we're saying from keras.preprocessing import sequence. Again, we're treating our text data as a sequence, as we've talked about. We're going to say sequence.pad sequences trained data, and then we define the length that we want to pad it to. So that's what this will do. It will perform these steps that we've already talked about. And again, we're just going to assign test data and trained data to, whatever this does for us. We can pass the entire thing. It'll pad all of them for us at once. Okay, so let's run that. And then let's just have a look at, say, trained data 1 now, because remember this was length 189, right? So if we look at trained data, so train_data 1, like that, we can see that it's an array with a bunch of zeros before, because that is the padding that we've employed to make it the correct length. Okay, so that's padding. That's something that we're probably going to have to do most of the time when we feed something to our neural networks. All right, so the next step is actually to create the model. Now this model is pretty straightforward. We have an embedding layer, an LSTM, and a dense layer here. So the reason we've done dense with the activation function of sigmoid at the end is because we're trying to pretty much predict the sentiment of this, right? Which means that if we have the sentiment between 0 and 1, then if a number is greater than 0.5, we could classify that as a positive review. And if it's less than 0.5 or equal, whatever you want to set the bounds at, then we could say that's a negative review. So sigmoid, as we probably might recall, squishes our values between 0 and 1. So whatever the value is at the end of the network will be between 0 and 1, which means that, we can make the accurate prediction. Now here, the reason we have the embedding layer, you're like, well, we've already pre-processed our review, is even though we've pre-processed this with these integers, and they are a bit more meaningful than just our random lookup table that we've talked about before, we still want to pass that to an embedding layer, which is going to find a way more meaningful representation for those numbers than just their integer values already. So it's going to create those vectors for us, and this 32 is denoting the fact that we're going to make the output of every single one of our embeddings or vectors that are created 32 dimensions, which means that when we pass them to the LSTM layer, we need to tell the LSTM layer it's going to have 32 dimensions for every single word, which is what we're doing. And this will implement that long short-term memory process we talked about before and output the final output to tf.keras.layers.dense, which will tell us, that's what this is, right? It'll make the prediction. So that's what this model is. We can see, I'm going to give this a second to run here, the model summary, which is already printed out. We can look at the fact that the embedding layer actually has the most amount of parameters because essentially it's trying to figure out, all these different numbers. How can we convert that into a tensor of 32 dimensions, which is not that easy to do. And this is going to be the major aspect that's being trained. And then we have our LSTM layer. We can see the parameters there, and our final dense layer, which is 8, getting 33 parameters. That's because the output from every single one of these dimensions, 32, plus a bias node, right, that we need. So that's what we'll get there. You can see model.summary. We get the sequential model. Okay. So training. So now it's time to compile and train the model. You can see I've already trained mine. What I'm going to say here is if you want to speed up your training, because this will actually take a second, and we'll talk about why we pick these things in a minute, is go to runtime change runtime type and add a hardware accelerator of GPU, what this will allow you to do is utilize a GPU while you're training, which should speed up your training by about 10 to 20 times. So I probably should have mentioned that beforehand, but you can do that, and please do for these examples. So model.compile. All right, so we're compiling our model. We're picking the loss function as binary cross entropy. The reason we're picking this is because this is going to essentially tell us how far away we are from the correct probability, right? Because we have two different things we could be predicting. So, either 0 or 1, so positive or negative. So this will give us a correct loss for that kind of problem that we've talked about before. The optimizer, we're going to use RMS prop. Again, I'm not going to discuss all the different optimizers. You can look them up if you care that much about what they do. And we're going to use metrics as ACC. One thing I will say is the optimizer is not crazy important. For this one, you could use Atom if you wanted to, and it would still work fine. My usual go-to is just use the Atom optimizer unless you think there's a better one to use. But anyways, that's something to mention. Okay, so finally, we will fit the model. We've looked at this syntax a lot before, so model.fit. We'll give the training data, the training labels, the epochs, and we'll do a validation split of 20%. So that's what 0.2 stands for, which means that what we're going to be doing is using 20% of the training data to actually evaluate and validate the model as we go through. And we can see that after training, which I've already done, and you guys are welcome to obviously do on your own computer, we kind of stall at an evaluation accuracy of about 88%, whereas the model actually gets overfit to about 97-98%. So what this is telling us essentially is that we don't have enough training data, and that after we've even done just one epoch, we're pretty much stuck on the same validation accuracy, and that there's something that needs to change in the model to make it better. But for now, that's fine. We'll leave it the way that it is. Okay, so now we can look at the results. I've already did the results here just to, again, speed up some time, but we'll do the evaluation on our test data and test labels to get a more accurate kind of result here. And that tells us we have an accuracy of about 85.5%, which, isn't great, but it's decent considering that we didn't really write that much code to get to the point that we're at right now. Okay, so that's what we're getting. The model's been trained. Again, it's not too complicated, and now we're on to making predictions. So the idea is that now we've trained our model, and we want to actually use it to make a prediction on some kind of movie review. So since our data was pre-processed when we gave it to the model, that means we actually need to process anything we want to make a prediction on in the exact same way. We need to use the same lookup table. We need to encode it, precisely the same. Otherwise, when we give it to the model, it's going to think that the words are different, and it's not going to make an accurate prediction. So what I've done here is I've made a function that will encode any text into, the proper pre-processed kind of integers, right? Just like our training data was pre-processed, that's what this function is going to do for us, is pre-process some line of text. So what I've done is actually gotten the lookup table, so essentially the mappings from IMDb, if I could read that properly, from that data set that we loaded earlier. So let me go see if I can find where I defined IMDb. You can see up here, so keras.datasets import IMDb. Just like we loaded it in, we can also actually get all of the word indexes, or that map. We can actually print this out if we want to look at what it is after. But anyways, we have that mapping, which means that all we need to do is keras.preprocessing.text to word sequence. What this means is given some text, convert all of that text into what we call tokens, which are just the individual words themselves. And then what we're going to do is just use a kind of for loop inside of here that says word index at word, if word in word index, else 0 for word in tokens. Now what this means is essentially if the word that's in these tokens now is in our mapping, so in that vocabulary of 88,000 words, then what we'll do is replace its location in the list with that specific word, or with that specific integer that represents it. Otherwise, we'll put 0 just to stand for, we don't know what this character is. And then what we'll do is return sequence.pad sequences, and we'll pad this token sequence and just return actually the first index here. The reason we're doing that is because this pad sequences works on a list of sequences, so multiple sequences. So we need to put this inside a list, which means that this is going to return to us a list of lists. So we just obviously want the first entry because we only want, that one sequence that we padded. So that's how this works. Sorry, that's a bit of a mouthful to explain, but you guys can run through and print this stuff out if you want to see how all of it works specifically. But yeah, so we can run this cell and have a look at what this actually does for us on some sample text. So that movie was just amazing, so amazing. We can see we get the output that we were kind of expecting. So integer encoded words down here, and then a bunch of zeros just for all the padding. Now, while we were at it, I decided why don't we make a decode function so that if we have any movie review like this that's in the integer form, we can decode that into the text value. So the way we're going to do that is start by reversing the word index that we just created. Now, the reason for that is the word index we looked at, which is this, right, goes from word to integer. But we actually now want to go from integer to word so that we can actually translate a sentence, right? So what I've done is made this decode integers function. We've set the padding key as 0, which means that if we see 0, that's really just means, nothing's there. We're going to create a text string, which we're going to add to. And I'm just going to say for num in integers. Integers is our input, which will be a list that looks something like this, or an array, whatever you want to call it. We're going to say if number does not equal pad. So essentially, if the number is not 0, right, it's not padding, then what we'll do is add the lookup of reverse word index num, so whatever that number is, into this new string plus a space, and then just return text :-1, which means return everything except the last space that we would have added. And then if I print the decode integers, we can see that this encoded thing that we had before, which looks like this, gets encoded by the string that movie was just amazing, so amazing. Sorry, not encoded, decoded, because this was the encoded form. So that's how that works. Okay, so now it's time to actually make a prediction. So I've written a function here that will make a prediction on some piece of text as the movie review for us. And I'll just walk us through quickly how this works, and then I'll show us the actual output from our model, making predictions like this. So what we say is we'll take some parameter text, which will be our movie review, and we're going to encode that text using the encode text function we've created above. So just this one right here that essentially takes our sequence of, words. We get the pre-processing, so turn that into a sequence, remove all the spaces, whatnot, get the words. Then we turn those into the integers, we pad that, we return that. So here we have our proper pre-processed text. Then what we do is we create a blank NumPy array that is just a bunch of zeros that's in the form 1 to 50, or in that shape. Now the reason I'm putting in that shape is because the shape that our model expects is something 250, which means some number of entries and then 250 integers representing each word, right? Because that's the length of a movie review, is what we've told the model is the length 250. So that's the length of the review. Then what we do is we put pred 0, so that's what's up here, equals the encoded text. So we just essentially insert our one entry into this array we've created. Then what we do is say model.predict on that array and just return and print the result 0. Now, that's pretty much all there is to it. I mean, that's how it works. The reason we're doing result 0 is because, again, model is optimized to predict on multiple things, which means like I would have to do, list of encoded text, which is kind of what I've done by just doing this prediction lines here, which means it's going to return to me an array of arrays. So if I want the first prediction, I need to index 0 because that will give me the prediction for our first and only entry. All right, so I hope that makes sense. Now we have a positive review I've written and a negative review, and we're just going to compare the analysis on both of them. So that movie was so awesome, I really loved it and would watch it again because it was amazingly great. And then that movie sucked, I hated it and wouldn't watch it again. It was one of the worst things I've ever watched. So let's look at this now. And we can see the first one gets predicted at 72% positive, whereas the other one is 23% positive. So essentially what that means is that, if the lower the number, the more negative we're predicting it is. The higher the number, the more positive we're predicting it is. If we wanted to not just print out this value, and instead what we wanted to do was print out, positive or negative, we could just make a little if statement that says, if this number is greater than 0.5, say positive, otherwise say negative, right? And I just want to show you that changing these reviews ever so slightly actually makes a big difference. So if I remove the word awesome, so that movie was so, and then I run this, you can see that oh wow, this actually increases and goes up to 84%, right? So the presence of certain words in certain locations actually makes a big difference, and especially when we have a shorter length review, right? If we have a longer length review, it won't make that big of a difference, but even the removal of a few words here, and let's see, so removing the word awesome changed it by almost like 10%, right? Now if I move so, let's see if that makes a bigger difference. It makes a very little difference because it's learned, at least the model, right, that the word so doesn't really make a huge impact into the type of review. Whereas if I remove the word I, let's see if that makes a big impact. Probably not, right? No, it goes back up to 84. So that's cool, and that's something to play with, is removing certain words and seeing how much impact those actually carry. And even if I just add the word great, like would, great, watch it again, just in the middle of the sentence, doesn't have to make any sense. Let's look at this here. Oh, boom, we increase like a little bit, right? And let's say if I add this movie you really sucked, let's see if that makes a difference. No, that just reduces it like a tiny bit. So something cool, something to play with. Anyways, now let's move on to the next example. So now we're on to our last and final example, which is going to be creating a recurrent neural network play generator. Now this is going to be the first kind of neural network we've done that's actually going to be creating something for us. But essentially what we're going to do is make a model that's capable of predicting the next character in a sequence. So we're going to give it some sequence as an input, and what it's going to do is just simply predict the most likely next character. Now there's quite a bit that's going to go into this, but the way we're going to use this to predict a play is we're going to train the model on a bunch of sequences of text from the play Romeo and Juliet, and then we're going to have it so that we'll ask the model, we'll give it some starting prompt, some string to start with, and that'll be the first thing we pass to it. It will predict to us what the most likely next character for that sequence is, and we'll take the output from the model and feed it as the input again to the model and keep predicting sequence of characters. So keep predicting the next character from the previous output as many times as we want to generate an entire play. So we're going to have this neural network that's capable of predicting one letter at a time actually end up generating an entire play for us by running it multiple times on the previous output from the last iteration. Now, that's kind of the problem. That's what we're trying to solve. So let's go ahead and get into it and talk about what's involved in doing this. So the first thing we're going to do obviously is our imports. So from keras.preprocessing, import sequence, import keras, we need TensorFlow, NumPy, and OS. So we'll load that in. And now what we're going to do is download the file. So the data set for Romeo and Juliet, which we can get by using this line here. So Keras has this utils thing, which will allow us to get a file, save it as whatever we want. In this case, we're going to save it as shakespeare.txt, and we're going to get that from this link. Now, I believe this is just some like shared drive that we have access to from Keras. So we'll load that in here, and then this will simply give us the path on this machine, because remember, this is Google Collaboratory, to this text file. Now, if you want, you can actually load in your own text data, so we don't necessarily need to use the Shakespeare play. We could use anything we want. In fact, an example that I'll show later is using the B-movie script. But the way you do that is run this block of code here, and you'll see that it pops up this thing for choose files. Just choose a file from your local computer, and then what that will do is just save this on Google Collaboratory, and then that will allow you to actually use that. So make sure that's a text file that you're loading in there, but regardless, that should work, and then from there you'll be good to go. So if you don't need to do that, you can just run this block of code here if you want to load in the Shakespeare TXT, but otherwise you can load in your own file. Now, after we do that, what we want to do is actually open this file. So remember, that was just saving the path to it. So we'll open that file in RB mode, which is read bytes mode, I believe. And then we're going to say .read. So we're going to read that in as an entire string. we're going to decode that into UTF-8 format, and then we're just printing the length of the text or the amount of characters in the text. So if we do that, we can see we have the length of the text is 1.1 million characters approximately. And then we can have a look at the first 250 characters by doing this. So we can see that this is kind of what the plate looks like. We have whoever's speaking, colon, then some line, whoever's speaking, colon, some line, and there's all these break lines, so backslash ends, which are telling us, you know, go to the next line, right? So that's going to be important because we're going to hope that our neural network will be able to predict things like break lines and spaces and even this kind of format as we teach it more and get further in. But now it's time to talk about encoding. So obviously all of this text is in text form. It's not pre-processed for us, which means we need to pre-process it and encode it as integers before we can move forward. Now, fortunately for us, this problem is actually a little bit easier than the problem we discussed earlier with encoding words, because what we're going to do is simply encode each character in the text with an integer. Now, you can imagine why this makes this easier, because there really is a finite set of characters, whereas there's kind of an indefinite, or, you know, I guess infinite amount of words that could be created. So we're not really going to run into the problem where, you know, two words are encoded with such or two characters are encoded with such different integers that it makes it difficult for the model to understand, because, I mean, we can look at what the value of vocab is here. We're only going to have so many characters in the text, and for characters, it just doesn't matter as much because, you know, an R isn't like super meaningful compared to an A. So we can kind of encode in a simple format, which is what we're going to do. So essentially, we need to figure out how many unique characters are in our vocabulary. So to do that, we're going to say vocab equals sorted set text. This will sort all of the unique characters in the text. And then what we're going to do is create a mapping from unique characters to indices. So essentially, we're going to say UI for IU in a enumerate vocabulary. What this will do is give us essentially 0, whatever the string is, 1, whatever the string is, 2, whatever the string is, for every single letter or character in our vocabulary, which will allow us to create this mapping. And then what we'll do is just turn this initial vocabulary into a list or into an array so that we can just use the index at which a letter appears as the reverse mapping. So going from index to letter rather than letter to index, which is what this one's doing here. Next, I've just written a function that takes some text and converts that to an int, or the int representation for it, just to make it a little bit easier for us as we get later on in the tutorial. So we're just going to say np.array of, in this case, and we're just going to convert every single character in our text into its integer representation by just referencing that character and putting that in a list here, and then obviously converting that to numpy array. So then if we wanted to have a look at how this works, we can say text as int equals text to int text. So remember, text is that entire loaded file that we had above here. So we're just going to convert that to its integer representation entirely using this function. And now we can look at how this works down here. So we can see that the text for citizen, which is the first 13 letters, is encoded by 18, 47, 56, 57, 58, 1, and obviously each character has its own encoding, and you can go through and kind of figure out what they are based on the ones that are repeated, right? So that is how that works. Now, I figured while we were at it, we might as well write a function that goes the other way, so into text. The reason I'm trying to convert this to a numpy array first is just because we're going to be passing in different objects potentially in here. So if it's not already a numpy array, it needs to be a numpy array, which is kind of what this is doing. Otherwise, we're just going to pass on that. We don't need to convert it to a numpy array if it already is one. We can just join all of the characters from this list into here. So that's essentially what this is doing for us. It's just joining into text. And then we can see if we go into text, text is int colon 13, that translates that back to us for citizen. I mean, you can look more into this function if you want, but it's not that complicated. Okay, so now that we have all of this text encoded as integers, what we need to do is create some training examples. It's not really feasible to just pass the entire, 1.1 million characters to our model at once for training. We need to split that up into something that's meaningful. So what we're actually going to be doing is creating training examples where we have the first, where the training input, right? So the input value is going to be some sequence of some length. We'll pick the sequence length. In this case, we're actually going to pick 100. And then the output, or the expected output, so I guess like the label for that training example, is going to be the exact same sequence shifted right by one character. So essentially, I put a good example here. Our input will be something like hell, right? And then our output will be ELLO. So what it's going to do is predict this last character essentially, and these are what our training examples are going to look like. So the entire beginning sequence, and then the output sequence should be that beginning sequence minus the first letter, but tack on what the last letter should be. So that this way we can look at some input sequence and then predict that output sequence, that, you know, plus a character, right? Okay, so that's how that works. So now what we're going to do is define a sequence length of 100. We're going to say the amount of examples per epoch is going to be the length of the text divided by the sequence length plus 1. The reason we're doing this is because for every training example, we need to create a sequence input that's 100 characters long, and we need to create a sequence output that's 100 characters long, which means that we need to have 101 characters that we use for every training example, right? Hopefully that would make sense. So what this next line here is going to do is convert our entire string data set into characters. And it's actually going to allow us to have a stream of characters, which means that it's going to essentially contain, you know, 1.1 million characters inside of this tf.dataset object from tensor slices. That's what that's doing. Next, so let's run this and make sure this works all right. What we're going to do is say sequences is equal to char dataset.batch. Sequence length is the length of each batch, so in this case 101, and then drop remainder means, let's say that we have, you know, 105 characters in our text. Well, since we need sequences of length 101, we'll just drop the last 4 characters of our text because we can't even put those into a batch. So that's what this is doing for us, is going to take our entire character data set here that we've created and batch it into length of 101, and then just drop the remainder. So that's what we're going to do here. That's what sequences does. Now split input target. What this is going to do essentially is just create those training examples that we needed. So taking these sequences of 101 length and converting them into the input and target text, and I'll show you how they work in a second. We can do this, convert the sequences to that by just mapping them to this function. So that's what this function does. So if we say sequences.map and we put this function here, that means every single sequence will have this operation applied to it, and that will be stored inside this dataset object. Or I guess you could say object, but we'll also just say it's going to be, you know, the variable, right? So if we want to look at an example of how this works, we can kind of see. So it just says example. The input will be first citizen. Before we proceed any further, hear me speak. All speak, speak. First citizen you, and the output, notice the first character is gone, starts at I, and the last character is actually just a space here, whereas here it didn't have a space. So you can see there's no space. Here there is a space. That's kind of what I'm trying to highlight for you. The next example, we get are all resolved rather to die rather than famine, whatever. It goes to here, right? And then we can see here we omit that A, and the next letter is actually a K, right? That's added in there. So that's how that works. Okay, so next we need to make training batches. So we're going to say the batch size equals 64. The vocabulary size is the length of the vocabulary, which, if you remember all the way back up to the top of the code, was the set, or the sorted set of the text, which essentially told us how many unique characters are in there. The embedding dimension is 256, the RNN units is 1024, and the buffer size is 10,000. What we're going to do now is create a data set that's shuffled. So we're going to switch around all these sequences so they don't get shown in the proper order, which we actually don't want. And then we're going to batch them by the batch size. So if we haven't kind of gone over what batching and all this does before, I mean, you can read these comments. This is straight from the TensorFlow documentation. What we want to do is feed our model 64 batches of data at a time. So what we're going to do is shuffle all of the data, batch it into that size, and then again, drop the remainder if there's not enough batches, which is what we'll do. We're going to define the embedding dimension, which is essentially how big we want every single vector to represent our words are in the embedding layer. And then the RNN units, I won't really discuss what that is right now, but that's essentially how many. It's hard to really I'm just going to omit describing that for right now because I don't want to butcher an explanation. It's not that important. Anyways, okay.